We're very, very happy to be back 18 months later. In fact, we used the previous Storage Field Day as the platform from which we launched our company, came out of stealth mode, and we've had a lot going on over the last 18 months. So we're happy to be back and to give you an update. So we have 4 parts to this talk. I'll give a very brief company update, business on the business side, because I know most of you care mainly about technology. And then we will do a evolution of architectures talk. And you'll see exactly what we mean by that. It'll be mainly theoretic. And right after that, I'll turn it over to Howard Marks to give learnings since launch, what we learned over the last 18 months, and what we brought to market subsequently after the initial launch. And then Jeff Denworth will take it and give you a very small glimpse into the future, what we call Lightspeed, which is our new AI platform, not yet announced. Let's start. The company update. This is our timeline. We were founded back in 2016, as you may or may not remember. Last time we were on was our stealth mode exit after quite a few dozens of end user trials and a few months after we officially announced a GA product. And then over the last 18 months, we've deployed hundreds of petabytes of new capacity into production environments for our customers. My part will be focused mainly on what we did in 2016, which is around the innovation parts of building a new architecture. And then Howard and Jeff will talk more about the last year and a half. Fastest growing storage company in history. When we came out with a bang. And now after our first full year of revenue, we can say that we are just accelerating as fast as possible. On the left side of this slide here, you see a few of the companies that we admire, companies that came before us, Data Domain, Isilon, Pure Storage, Nutanix, and we present our revenue in this first full year compared to theirs. As you can see, just about equal to all 4 of them combined. And then on the right-hand side, a new funding announcement that came out just a few months ago gave us unicorn status, basically a company worth more than $1 billion. And so if we measure how long it took from the initial date of general availability to that status, we are fastest out of these companies that became unicorns before us. In fact, we now have another $100 million worth of funding invested in the company. Some companies raise money when they absolutely have to. We did it before we actually needed to. In fact, the entirety of our round B is still in the bank. And so we now have $140 million that makes up our war chest. It gives us a clear path to break even. In fact, the plan says that we will break even a lot faster than those other companies did from the previous slide. And it gives us this hefty new valuation that comes with a lot of responsibility. Our backers include Goldman Sachs, Norwest, as they always have. And we have a couple new investors. Next 47 led this last round, and NVIDIA, which Jeff will also be mentioning, is a very, very important partner of ours, now also an investor in the company. Basically, what this means is that we are building an independent company and that we're here to stay. We're here to stay for the very long term in order to support our customers and in order to keep innovating as we have so far. Let's talk a little bit about architectures and about innovation. In fact, going back in time, as I said, to 2016 when we started, throughout that year, we didn't write too much code. We basically took our time to get the architecture right. And we believe strongly that that is what allowed us subsequently to develop a system very, very quickly, and that looks very different than those of our competitors. Everyone, when mentioning storage field day, talks to me about the legendary talk that Dave Wright gave, Dave Wright from SolidFire, where he compared 3 architectures. He compared SolidFire to Extreme IO to Pure Storage. I'm not going to do that because I don't know enough about our competition to go into that level of detail. I also don't believe that looking to the sides is beneficial. It subconsciously makes us be more like our competition rather than innovating based on first principles. And so instead, what we thought to do is to look at the commonality of all of our competitors. And it turns out that at a conceptual level, they're all based on a shared nothing architecture. Way back when, 20 years ago, we had dual controller architectures. At some point about 10 years ago, those got stuck. They couldn't grow anymore in performance. And so scale out became the standard. And scale out is today synonymous with shared nothing. What we are here to do is to show you, A, why shared nothing architectures are now getting stuck. They can't grow anymore. And B, what can we do about that in terms of fixing it and providing a much better architecture for our customers. And so how do you start to solve a problem? How does innovation happen? I'm a strong believer, and here at VAST, we believe that you have to fully understand the problem and the problematic parts in whatever is state of the art at that point in time. And so let's do a brief understanding of shared nothing architectures, and what sets them apart, and what issues we have with them that we would like to overcome.
Renen, sorry, I have
Yes.
a couple of questions very quickly. So
Of course.
one of the biggest problems with the scale-out architecture usually is complexity. I mean, enterprise users, especially enterprise users, are very afraid to move from a single box that they understand. It's there since forever, and moving to a very complex node, configuration and everything. Another thing is the minimum amount of storage that you need, minimum amount of nodes that you need to start a scale-out infrastructure. Okay, minimum 3, 4, 5 nodes depending on the architecture. So, can you give a little bit of an idea on how you are addressing these 2 problems? So, minimum size, if it's something that you want to address as a market, and at the same time complexity from the front end. I mean, at least.
Sure. So you said it exactly right. Complexity is the enemy of scale out. And you'll see as I progress through these slides how we simplify what the architecture looks like, and in turn simplify our customers' lives. Our architecture, in fact, has a lot less parts to it, and has a lot less to manage as a result. And in terms of where you can start, you're exactly right. Existing scale-out architectures usually start with 3 nodes, 5 nodes. And to that effect, what we did is we brought it all the way down to a single node. You can start with 1. You obviously don't have high availability if you only have 1, but you can start with 1 and you can access all of your data, and that's just fine. If you want redundancy, you add another one. If you want more redundancy, you add another one. And the simplicity of adding nodes to our system is another point of pride, because it's all in software. It's all Docker containers. And so it's very easy to add nodes as you would like, especially in cases where you already have some type of Kubernetes infrastructure to orchestrate your containers. Then it's something that you simply don't need to think about at all. Okay, but going back to shared nothing, what does it look like? A shared nothing architecture basically has a building block that's called a node. And that node has within it a CPU, some memory, some type of battery in order to back up that memory in case of power loss, and then a set of drives, whether they're hard drives or SSDs or a combination of both. There are, and today, if you look at all of our competitors, anybody else that does scale out file or scale out object, this is their architecture of choice. Whether you look at Isilon, whether you look at Pure FlashBlade, or any of the other systems that we compete with today. What are the problems with this architecture? The first one is it's very hard to make it fit. You have to choose a ratio between these different parts, between the amount of CPU you want for performance, the amount of SSDs versus hard drives you want in cases of hybrid systems, the amount of memory you want, and then you prescribe that node. But once you have it, you have to keep growing with that node. And so you, in effect, choose your trajectory of ratio between capacity and performance, and you have to keep growing at that ratio on that trajectory. That's very problematic, especially today as workloads are adapting and changing and requirements change so dynamically. It's virtually impossible to say what you will need a year from now or 2 years from now.
Hey, Renen.
Yes, go ahead.
Some of the scale out solutions don't require, homogeneous nodes of storage and CPU and memory and that sort of stuff. Now, I would say it's not clear that most of those solutions have to have homogeneous nodes.
What happens when you don't have homogeneous nodes is that you get stuck on the resource that you have the limited amount of. So in a shared nothing architecture, the system is as powerful as the least powerful node times the number of nodes, because everything gets distributed evenly across nodes. And so if you have one node, one chain, one link in the chain that isn't as strong as the rest of them, you have an effect of everybody going down to the least common denominator. So you don't have to have all of these nodes look exactly the same, but if you don't, then you're wasting resources. And if you do, you're also wasting resources because a year from now, you don't need as much capacity or as much performance, but you have to keep paying for it. Otherwise, you're wasting resources for the other reason. And so you're between a rock and a hard place when you're trying to build these scale out, these shared nothing architectures, if you want them to be future proof.
Okay.
You don't like my answer.
Most of your, I'll call it competition, don't state that you're getting the least common denominator of a scale out cluster.
So most of the competitors will let you have dissimilar nodes, but a pool has to be all of the same nodes, and then they'll move data from pool to pool. But within the performance pooling happens among nodes with a very limited range of differences.
I'll accept that, Howard.
Thank you, Howard. That was me calling a friend to save me. Okay. What else is wrong with shared nothing architectures? What else do we want to improve? Data movement. The way a shared nothing architecture works is you have all of these nodes, and now they need to communicate one with the other. And the reason is that by the virtue of its name, shared nothing, each of these nodes has a certain slice of the pie, a certain responsibility for a piece of the namespace. And if I'm one node and I get a request for something that I'm not responsible for, which is usually the case, I need to ask another node to perform that operation on my behalf. And so data movements are constant in a shared, between nodes in a shared nothing environment. And that usually causes performance issues. Data copies, data movements, communications between nodes, all of that adds to latency and reduces our overall performance. That is usually solved with a cache. And cache is evil in our mind. You have two types of cache, write cache and read cache. Write caches are dangerous. You write something to a certain node and it doesn't actually propagate it down to the place that it's supposed to be. It just keeps it in cache, acknowledges that write, and reduces latency, but adds a lot of risk. What happens if there's a power failure? Now you need to dump all of that cache down to a persistent location. And so you need a battery to protect you. Those batteries fail often. Those procedures of dumping down, destaging cache data in cases of failures are error prone, and a lot of bugs exist in those types of processes.
Right. I never ran in this, right. I never considered cache evil. So I'm just trying to, so yeah, write cache has the power fail problem. Read cache, it's you know, it's a normal source of advantage to a number of these architectures to have cache.
I think it is an advantage to these architectures because it's overcoming a deficiency that they have, which is low performance, but at the same time, it's introducing a set of new problems that need to be solved. Our aim is not to say you don't need cache in these architectures, you do. Our aim is to say, can we build an architecture that doesn't require a cache such that we solve these problems not by adding complexity, but by removing complexity? And I'll show that. So write cache is, as we said, #1 contributor to enterprise storage data loss by far. And so if you can get rid of that and do something different without it, without hurting performance, that would be a good thing. On the read cache side, there's a problem of cache coherency. We have now 4 nodes and each one of them has a cache. What if somebody else changed it? Because remember, there's only a certain node that is responsible for each piece of data. And so if it gets read from another node that caches it such that it doesn't need to communicate with the owner, we now have a cache coherency problem. And cache coherency doesn't scale. It means everyone needs to talk to everyone in order to understand when data gets changed. And that is a big problem with shared nothing architectures, because as you add more nodes, you get diminishing returns in terms of performance. So solving performance causes us to limit our scale. And in fact, if you look at shared nothing architectures from our competitors, they're always capped at a certain number of nodes. In some cases, after you reach that number of nodes, you can still add more for capacity, but you can't add more for performance. In other cases, it's just a fixed number that you can't overcome.
Renen,
Yes.
many of these scale out solutions, 64 nodes, 32 nodes, 144 nodes, they don't really cap the number of nodes at something that, you know, yeah, I would consider 144 nodes more than adequate for most, you know, major organizations in the world, depending on the size of the nodes, stuff like that. Right?
I like that question. It depends on the size of the node. And that is the way that they're trying to solve this exponential increase in data. But we're capped at 144 nodes. By the way, it doesn't really work well when you get up to those levels of numbers of nodes for this reason. But it's capped at 144 nodes. And then as data grows and as capacity requirements increase, the only option for these architectures is to build bigger and bigger nodes. And that's another problem with shared nothing architectures, that nodes fail. And when a single node fails and it has 10 petabytes, 100 petabytes of capacity in it, that is a major event. Even with hundreds of terabytes inside a single node, that is a major event that in some cases, and if you talk to anyone that went through node failures with Isilon as an example, they will tell you that the rebuild can take months to recover from. It means that now all of these other nodes need to run a very heavy process of rebuilding all of that information, not because the media failed, but because the node became inactive. And so the more capacity you put behind each one of these nodes, the bigger risk you take on yourself. And the big problem with this is not just that during this process performance is degraded, but that you're at risk of another node failure. And until you complete this sometimes month-long process, if you have another node failure, then the system is down. Again, depending on how much resiliency that specific system has, but the best way to add resiliency is to reduce the time that it takes to recover redundancy. And the best way, or the optimal reduction, is to bring it down to 0, which, as you'll see in our architecture in shared everything, there is no process that needs to run when a node fails. And so you're at absolute maximum redundancy all of the time. That brings us to algorithmic trade-offs. And in this case, you have 3 pieces to a system, maybe 4 pieces if I take into consideration what Howard said before about pools of nodes within a cluster. But just to simplify, let's say there are 3 pieces in a system. The smallest piece is a drive, and then the drives are in nodes, and then the nodes are part of a cluster. And algorithms in these systems tend to be one of 2. They're either a global algorithm, but done at the node level, like we just saw in the previous slide, where a node fails, and so the nodes protect each other. Or they're a local algorithm done within the node, but not at fine granularity, but not at the cluster level. And that's, we can take an example from a company that I was previously at, Extreme.io, where the resiliency is done between drives, but inside a single shelf, inside a single node, not globally. You can see the same type of trade-off wherever you look. If you look at data reduction, you either do fine-grained compression that is local in nature, or you do global deduplication that is coarse granularity. All of these algorithms are one or the other, a clear trade-off that is imposed by this type of architecture. Okay, how do we fix this? And back in 2016, when we started, this was the question that we posed to ourselves. And I am going to walk you through a path that we took. I'll just say that the real path we took was a lot messier. There were a lot of ideas that were thrown out that didn't work out. There were a lot of paths that we tried progressing on that we ended up not choosing. But this is the culmination of that work. How do you design a new type of architecture? So the first thing that everyone will tell you today in 2020 is disaggregation. Disaggregation is becoming a very popular word. It's the next level beyond hyperconverged. And disaggregation is a very important piece of this next architecture, but it's not enough. If you just do disaggregation, you're not accomplishing nearly enough to overcome all of the challenges that we just mentioned. In fact, in most cases where you see disaggregation happening, it's a shelf with a lot of SSDs that is detached from the CPU, which is a good thing. But in most of those cases, that shelf contains single ported SSDs and has, and in effect becomes a single point of failure. If you do that, you not only don't solve these problems, but you add a new problem, because now when one of these shelves fails, it's not one node that failed, it's 3 nodes that failed or 4 nodes that failed, because that shelf holds all of that capacity for multiple nodes. So disaggregation in and of itself is not enough. It keeps that tight relationship between CPU and memory and SSDs, even though the SSDs are on the other side of the network. Another problem is the problem that we talked about, flexibility of growth. If you have dedicated SSDs to each one of these nodes, then you need to grow together. You can't grow grow CPUs at a different trajectory than you are growing SSDs, because that will cause an imbalance in the system. And so it's a good first step. It allows you to start thinking about these two are separate resources, but it is only that first step.
Question. Would you categorize VAST as a hyperscaler or a hyper-converged?
I wouldn't categorize us as either, because I don't fully understand the difference between those two terms. But it's definitely a hyperscale architecture in the sense that we can scale it up not to 144 nodes, but to tens of thousands and hundreds of thousands of nodes. It's hyper-converged in the sense that all of these nodes eventually, as we will see in a few minutes, are software, and they can run on the same servers as other applications do. And so we borrow ideas from different architectures that work, and we try to eliminate the ideas that didn't work. It's also hyper-converged and hyperscale in the sense that you have a single network. You no longer have a separate network for your storage and for your compute and to connect the two. It's a single fabric that is very strong that allows this architecture. But it's not hyper-converged in the sense that it's disaggregated. These SSDs do sit in a separate physical location than the CPU itself. Shared everything. Shared everything is the real key here. Rather than having, once you have those SSDs accessible to everyone, why do you want to paint them in a certain node's color? You don't. You want all of your nodes to be able to access all of your SSDs across this shared fabric. That obviously introduces a lot of rethinking. You now have all of the nodes accessing the same data structure. They all need to do so in a synchronized manner. They all need to be able to fail without actually having that data structure corrupted. And so a lot of things need to be done very, very differently to go to shared everything. While disaggregation was a very easy step and a step that we expect all of the competitors to be able to do, going to shared everything is where you gain all of the advantages, and that requires a blank sheet of paper. You can't retrofit an existing system that was designed as shared nothing into shared everything. And we now have a few fortuitous side effects. If it's shared everything, if each of these nodes can see the entirety of the namespace in a direct attached manner, even though it's on the other side of the network, then suddenly we don't need those RAM. We don't need the RAM anymore. We don't need the cache. We don't need the batteries. We don't need all of those bad things that introduce complexity and introduce risk because of Intel. And we are indeed a walking advertisement for Intel, specifically their Optane technology, which allows us to get rid of all of that complexity. It allows us to break free from caches. It allows us to break free from cache coherency. It allows us to keep all of the state within the enclosure and all of the logic up in the nodes. And that is true disaggregation. When you no longer have any state in the nodes, that's what we mean when we say disaggregation. And that's what we've done. And that, of course, requires a complete rethink of metadata structures, because that now they are in persistent media that is very, very fast. And now they need to be accessed by hundreds of thousands of nodes at the same time while maintaining consistent across the plane. The next very, very fortuitous side effect of this architecture is that you don't need those nodes to communicate anymore. They don't talk to each other. You basically eliminate any east-west traffic within those nodes, and that allows us to, again, be able to scale in a much, much better way than shared nothing architectures could. If you remember, what caused them not to be able to scale is the fact that there was so much crosstalk. And as you grow, that grows quadratically. And so we don't have that crosstalk. Everyone sees everything, can read and write directly to the media. And so we can scale up to very large levels. Now,
Renen, where's the metadata in this architecture?
it's right in that blue part that says Optane Intel.
And so how does a node know which of the QLC SSDs to talk to?
Right. So what we have is inside those Optane drives, it's metadata that is based on a fan-out tree with indirection. So it will be a few hops to Optane to understand which QLC drive to go to find your data. And we can accommodate those few hops because Optane is 5 to 10 microseconds in latency. And so let's say you have 5 of those, that's no more than 50 microseconds of continuous access to Optane across the network to understand where your data is, which drive you should read it from, which is perfectly fine. And the other side of that is that in order to understand which Optane to go to, where to start looking for that metadata structure is done with a function. It's a consistent hashing mechanism. We didn't invent it, but it allows us to, through logic, understand which Optane to go to first without needing to have multiple copies.
Renen, can I just
of course
pick up on a couple of things there? So if I hop between Optanes, just to pick on some semantics here, that's east-west traffic, right?
Oh, no,
Because-
not at all.
No, it is. That's a semantic. I'm just picking you up on the language you're using needs to be a little bit more, either less prescriptive, because you're using it to try and downplay the competition. No. I just want to finish what I'm saying. You're trying to use it to downplay the competition by saying cache is evil. We don't do east-west. But you're using Optane as a cache and you do east-west traffic. I don't have a problem with either of those things. But what you're saying is that's a bad thing to do, but we do it, just we don't say it that way. You're just manipulating the language, and I feel that that's a little bit disingenuous.
Jason,
let me clarify.
I wouldn't.
The part about write caches that were problematic was the battery backup. We eliminated the need for battery backup by moving that write cache or write buffer into persistent media.
Okay, but you didn't say that, and that's why I'm saying that if
that's
that
why I'm
answer is
clarifying.
so much better. If you had said that first, then I wouldn't have picked up on the point.
That's okay.
That's all I mean. So
That's okay. On the read cache side, we think those are bad because of cache coherency problems. We eliminated any type of read cache entirely. We always read directly from QLC. And so we eliminated read cache entirely, and we changed the write cache. We do call it a write buffer, but the main problem with that was the battery backup and the volatile media, which we don't have anymore.
yeah, okay, that's much clearer, and I think that's much fairer.
Sure. With respect to east-west traffic, the only thing I meant to say is that the compute nodes that you see on the top don't move data between them. And the data boxes that you see on the bottom also don't move data between them. The only direction where data gets moved is between a compute node and a data box and vice versa. So it's only up-down in this picture, which is what I meant by north-south versus east-west.
If my traffic hits one Optane and I'm not here, and it tells me to go to another one, how am I getting there? Is it going back north-south again extra and then that way?
That's correct.
Okay.
All of the logic is up in the compute nodes. And so you have to go back to the compute node and tell it won't tell it the data isn't there. It will tell it where to go down that tree to another Optane to look for the next level down. And then it keeps going north-south and finding that location.
How do you make that not super inefficient if I've got 1,000 nodes and I accidentally hit the last one?
Sure.
Because I have to go through
But
999 first. That's all.
No,
But Jason, you never hit a node that way. You hit a front end node and you make a request, a read, a write, a directory lookup, whatever. That front end node processes that request to completion. It looks in the consistent hash table, which tells it which Optane the metadata it's looking for is found. Then it looks in that Optane And then that optane may have pointers to another optane, which makes the node that you're connected to go look in that other optane. There's no forwarding of messages that have to be processed by somebody else.
Where's the hash table, Howard?
The consistent hash table is in Optane, but it gets loaded up into it's small, and so it gets loaded up into all of those front ends in the first hour of operation.
Would you call that cache?
Let me just correct Howard on that point. It's a pure function. It's a pure function that all it needs as input is which optanes are available at any given moment and the piece of metadata that you're looking for, and it will point you to the correct optane through that function.
So
And touche, Dave Chappa.
I'm missing this. You guys might have to dumb it down for the systems guy. There's metadata.
Usually whoever says that is the smartest person in the room. So now I'm a little scared.
So there's metadata and there's a directory tree. I have to know where my data is at. I can't go fishing for the data because that will be too inefficient for a system scale. What system, where's the centralized data set for that? When I hit a front end and say, hey, give me my latest CTO dose video, where's that file? Walk me through that.
So in NFS, that request comes as give me this byte range within a handle that specifies a file. The hash of that handle through the function defines a particular optane that has the root of the tree that describes that file.
It goes to the root of what needs to be done differently when moving to an architecture like this. And so a lot of our IP is around these pieces. Okay, now that we don't have any crosstalk, that opens up a whole new game. Now you don't need to have a single pool of CPUs. You can do CPU pooling. And these can be on separate networks. They don't talk to each other. What that gives you is workload isolation. Rather than needing separate pools that include the media in order to isolate workloads, you just need separate CPUs because the nodes, the CPUs, are the performance bottleneck, and you can share the media and you can share the data, and everyone can work on the same global namespace while not stepping on each other's toes, because each application or each group within the organization have their own dedicated nodes that they access the media through. And Howard will also give a demo of this.
So Renen I'm not sure what the right term, the Optane nodes, are they homogeneous or are they just, not heterogeneous nodes? Can I have different numbers of QLCs in each of these, or how does that work?
You could have, I'm sorry. There are two questions there. The question of ratio between QLC and Optane, today it's fixed. You only need about 1% to 2% of Optane to hold this metadata pieces that we need. The metadata structures also can the lowest level can go down into QLC if needed, and for the right buffers. But in terms of different types of QLC, different sized drives, I'll address that too. You can definitely have different sized drives across the cluster. And to be perfectly honest, it doesn't matter where the QLC drives are, where the Optane drives are. The whole enclosure piece is just an extension of the fabric. All we care of is to see a big list of SSDs that we can work with.
And all the QLC and the Optane SSDs are directly accessible to the fabric? I mean, it's like NVMe or?
That's exactly right. NVMe over fabrics. We support InfiniBand or Rocky over Ethernet.
All right, thanks.
Okay, what else do you gain? Resilience. Remember all those nodes that whenever one failed, there was a big problem, or whenever there was a power outage, there was a big problem. You don't have any of that anymore. Nodes can come up, they can go down. It doesn't matter. They're all stateless. Nothing needs to happen when a node comes up or goes down. When a path into one of these enclosures goes down, it's just a fabric problem. It's the same as if a switch went down. You can have a redundant fabric and it doesn't affect anything.
So you're trying to redefine the availability zone or the failure zone there?
I'm not sure I understand the difference.
Well, you're saying it doesn't matter. There's no single point of failure. There's no recovery time if a node goes down. So that is.
It's not just no single point of failure. It's no multiple point of failure. If you have 100 of these nodes, 99 of them can fail at the same time. You still have access to the entirety of the data set.
Well, yeah, that's what I'm asking, because you're trying to redefine the availability zone, and that's the architecture of availability zone is to minimize the failure damage. So if you're saying that you have such
we minimize it down to 0. These nodes are completely stateless.
Okay, I like we'll dive deep into that one.
Sure.
As my friend likes to say, we'll double click deep in that one.
Sure.
So the question, what is a node in this environment? Is the
Container.
Optane with it's a container? That's great. That's wonderful. That's software and it can go anywhere. I mean, the question is this shelf. Is this shelf a node with the Optane and the QLC? What do you call that?
The shelf is just a way for us to access the media.
But it's packaged in hardware. It exists in some
It's a JBOF.
frame.
It's a JBOF.
It's a JBOF.
A highly available JBOF.
And if the JBOF fails, the failure mode for a JBOF is that it's got a fabric disconnect. Is that how it works?
That is correct. It has 2 nodes on the back end that offer redundancy.
You're using the node word again.
I'm sorry. It has 2 canisters on the back end that offer redundancy. If you see this picture, each of these canisters has access to all of the drives. And so if a canister fails, you still have access to all of the drives through the other canister. And what I do here is I am basically saying that those canisters are very similar to Ethernet switches or InfiniBand switches. They're just an extension of the fabric that allows us access into the media.
And there's no power supply associated with the
Sure. You
shelf?
Have 4 power supplies.
JBOF?
You have 4 power supplies in that JBOF, and they're fully redundant. And if you lost all 4 of them at the same time, then you would lose access to those drives. Yes.
And in a sufficiently large system, if you chose that option, you could continue operating even after an entire enclosure goes offline.
Yes, because our resiliency codes in a large system, they're all across drives, and so they will be across drives, across enclosures. So you get an extra level of resiliency in large systems, but you don't pay for that inefficiency if you only want to buy a single shell.
Okay, thanks.
Of course.
Can I just ask on that, how many shelf enclosures can I replicate my data across? And is that configurable, or do I create a failure domain and say
once you get to 11, based on the current number of or stripe size, I should say, you should be able to sustain a full shell failure. So anything 11 or above.
But we don't break the system up. All of the enclosures make up one pool, and stripes get spread across all of them.
Correct.
And you don't have to control width. We take care of it.
Sure. Is there a limit to that? Is it if I got to
146 plus 4 is the widest width. The largest pool is theoretically thousands tested in tens.
Okay.
Now, this opens up the container world. Pets versus cattle. Stateless containers that can go up and go down. That sounds a lot like container world. Kubernetes. You now have, for the first time, the ability to have storage, which is stateful, fully aligned with microservices architectures in the data center. The last thing I'll say about this is asymmetric growth. It goes back to your question before, Ray, about different drives of different sizes. Because you grow drives independently from compute, you can add drives of different sizes, and we will make full use of the resource. You can add CPUs of different power, and we will make full use of the resource. And there's no balance that needs to happen. And in fact, as you progress, you can add disk-like parts to the same system. The other big advantage, of course, is that you can choose where you want to be in this performance capacity grid. You can choose to buy a lot of capacity or a little. And then with that, you can choose to deploy a lot of nodes, a lot of containers, or a little. And that can change dynamically as well. You can spin them up, you can spin them down as you would like. So full flexibility. You don't need to know what your workload will look like in the future. Asymmetric growth. You don't need to stay with something just because you bought it in 2020. You can always use state-of-the-art hardware to add to this same cluster.
Who are your customers today? What market are you guys targeting right now?
Scale out, file, and object is our market. Currently, we have customers across multiple types of workloads, mainly in places where you need a lot of capacity because we start in the petabyte range and we grow from there, and mainly in places where there's an importance to performance because we do give both in a world where it's very difficult to find storage system.
Do those customers care about the data protection piece of that? Or are they just looking at they're offloading a bunch of data there to do some processing, some analytics, and then they don't care about the data?
About data protection. This system is more resilient than anything else they can find, and that's a big reason that a lot of them choose us.
Sure, I'm talking about more of your traditional data protection from a compliance perspective, from versioning, catalog. How are customers protecting this massive data repository in that respect?
They can either take snapshots, which we introduced last year, or they can connect us using a standard backup system to another VAST box. They can also connect us using our own replication to cloud functionality and have the second copy not in their data center, but in a public cloud. Howard will discuss that piece. Okay. So we have the features and functionality that support that. And in some cases, we are also treated as a backup target ourselves because of the economics of this system.
So on the roadmap, I can see this being applicable in environments that I've worked in, like genomics, et cetera, where I need petabytes of data. However, I still need to back it up. Are you guys partnering with any of the ISVs currently? Because I know from an enterprise perspective, that's kind of a showstopper for me.
That's where I was getting.
Sure, we are partnering with the current ISVs. None of the partnerships are public yet, but we are, and we're deploying with them and we're working with them to provide customers that piece as well.
Is it a better together story or is it an integrated story?
It's a better together story. There's no integration.
All right, thank you.
Okay, economies of scale. This is the last piece, the algorithmic piece. Suddenly we have all of these nodes, all of these SSDs, and we no longer are confined to local fine-grained or global coarse-grained. And so the first thing we do is a new type of compression that is global on one hand, but goes all the way down to the bit and byte level on the other. The second thing we do is we choose exactly where to place data. This allows us to use very low cost flash, and we choose it all the way down to the erase block, but across the entire system. And we place it not in a time fashion the way a log structured system would, but based on predictive algorithms that tell us when data will be overwritten or deleted, such that we sustain the low write cycles of this low cost flash. And then it gets down to QLC in very wide stripes, again, enabled by this new type of algorithm that is locally decodable, globally encodable, locally decodable, again, leveraging the global nature of the system, but going down to very low levels of granularity when you want to do a recovery or a rebuild. And the combination of these three algorithms, they're all global, they're all fine-grained, exactly the opposite of what you could do in shared nothing, is what allows us to realize the true value of this new architecture and allows us to do the next thing, which I want to discuss. Okay, so that was an exposition of shared nothing architectures to shared everything. Why do we need a new architecture? What are the benefits of it? why the shared nothing architectures are stuck or are nearing that wall where they can't scale anymore, and why shared everything breaks through that wall and allows us to do things that weren't possible before. This, I think, was part of a question at the very beginning about complexity of large systems. And Ray also alluded to it when he talked about dislike parts and pools and tiering, whether it's inside a system or whether it's across systems, has always been complicated. The more problematic piece is that it doesn't work anymore. It doesn't work for new workloads. What do I mean by that? Tiering algorithms or caching algorithms, they work on one of two types of workloads. Either there's a very small data set that fits in the top tier, or there's a very predictable access pattern that we can bring stuff up into the top tier before it actually gets read. What happens now in these new AI workloads that Jeff will discuss, and basically analytics in general, and analytics is taking over traditional workloads as well because we want to analyze our data. What happens is data sets keep growing, and so they grow beyond that limited size of the first tier or of the cache, and they're becoming less predictable. They're becoming more and more random. And even if a single workload is fairly predictable, you want to analyze multiple things on the same data set at the same time, and then you get that IO blender effect, where one of those analyses could be predicted, but the combination of them cannot. And so caching or tiering doesn't work anymore. You can't find the algorithm that will predict what to place in that top tier. Now, even if you could, let's pretend that I have an oracle that gives me a miraculous caching algorithm that gets it right 99% of the time. It's still not good enough because IOs are dependent one upon the other. And if I have one IO that needs to go down to that bottom tier, everyone standing in line behind it, all of those IOs that are cache hits, are still suffering from its high latency. And so even if you do it 99% good, which is practically impossible, you still get the performance or the experience of the slow bottom tier. Now, the problem, of course, is that you have small, expensive media that's very fast and large, inexpensive media that's very slow. How do you come across that? How do you fix that? Well, the insight here is that low-cost flash breaks that trade-off. Low-cost flash isn't low-cost because it's small. It isn't low-cost because it's cheap, because it's less performant. It's low-cost because it's less endurant. And that's a very different thing. And so if we could find a way to use the low endurance flash, which I mentioned a few slides ago, then we can break this trade-off. Then we can get rid of caching, get rid of tiering, get rid of all of this complexity. And so it's a virtuous cycle of consolidation. You have the low-cost flash that doesn't have a lot of write cycles. And then you have archival data that doesn't need a lot of write cycles because it doesn't get changed very often. And so if you could use the low-cost flash, you can store archival data because it's cheap enough. And if you store archival data, you can use the low-cost flash because it doesn't need a lot of write cycles. And this is that virtuous cycle that allows us to break through this paradigm and give flash for archive. However, we don't want to store just the archival data. We want you to store all of your data on this system. And the second insight that allows us to do that is that endurance is amortized. When you have that 10 petabyte archive and it only uses one write cycle a year, or not even that, if it saves the data for 7 years, one write cycle every 7 years, you can use all of those unused PE cycles for more dynamic applications. And so breaking that or entering that virtuous cycle allows us to not just use the not just house the archival data, but to provide a single solution for all of your data. And another side effect of that is that performance is maximized. Now that you have 10 times more flash because of all of that archive capacity that you're putting on it, you're also getting 10 times more performance. And you can use all of that performance in whichever way you'd like across your applications. Bottom line, DASE, disaggregated shared everything. That's the ultimate realization, and tier consolidation becomes an imperative. One platform for all your data, infrastructure to consolidate all of your applications on via workload isolation of pools, highly resilient to enhance uptime, and we measure ourselves on uptime, and we are way above anything that other systems that we're familiar with ever were, and one tier to rule them all. You now have economies to democratize Flash for all of your data. You don't need all of that complexity anymore.
So Renen, just one question. You mentioned Docker containers somewhere in this thing. So the vast software functionality that runs in the stateless nodes, the CPUs, is actually a container?
That's right.
That's very interesting.
It's a container, and it can run on dedicated nodes if you like. It will also be able to run on the same nodes running the various applications and be orchestrated through the same Kubernetes platform that manages the rest of your applications. If you want more CPU for storage because you want more IO performance, spin up more containers. If you want to take that CPU and give it to another application because you're not IO bound right now, do that and do it dynamically and make the best use of all of your CPU power without silos.
So that container becomes an NFS client?
NFS server.
An NFS server. So clients would be talking to the container.
That's right.
I got you. Okay, thanks.
It's an NFS server, it's an SMB server, and it's an S3 server today.